So we've already seen some examples of simple Lewis structures that we were able to deduce by looking at the Lewis dot diagrams of individual elements. However, it's not always possible to determine Lewis structures in this way, and when that is the case, then we will move on to systematic methods for drawing Lewis structures, which I'm about to illustrate in this section. So when we draw a Lewis structure, what we are assuming is that the total number of valence electrons in a molecule are shared in such a way that each atom has a share of 8 electrons, or if it's hydrogen, that it has a share of 2 electrons. So the first step in our systematic procedure for drawing a Lewis structure is to count up the total number of valence electrons that we have to form all of the bonds and complete all of the atoms' octets. So for example, if I wanted to draw the Lewis structure for carbon tetrachloride, I would count up 4 electrons for the carbon, because carbon is in group 4A, and then I have 4 chlorine atoms, and each of those are in group 7A, so I would have 4 times 7 electrons for the chlorine atoms. So adding that together, 4 plus 4 times 7 gives me a total of 32 valence electrons to construct all of the bonds and to complete all of the octets of all of the atoms. The second step in the systematic procedure for drawing a Lewis structure is to determine the arrangement of atoms in our molecule or polyatomic ion. There are a few guidelines that help. Hydrogen is always going to be an outer atom. The element with the lower group number will be the central atom, since the lower a group number that an atom has, the more bonds it will form in order to obtain an octet. Occasionally you'll find that you have 2 elements in the same group, in which case you want to remember that the higher period number is the element with the higher period number is usually going to be the central atom, because it is bigger and it has more space to place all of the bonds around it. So for our carbon tetrachloride molecule, we'll take note that carbon is in group 4A, whereas chlorine is in group 7A. So carbon is going to go in the middle because it has the lower group number, and our chlorines will go on the outside since they have the higher group number. The next step is that we need to recognize that our outer atoms need to be connected to our central atom via at least a single bond. So we can go ahead and draw in single bonds connecting our outer atoms to our central atom. Now for every single bond that we draw in, we're going to be sharing 2 electrons. So we want to add up the number of electrons that we're sharing to get our basic structure and subtract that from the total number of valence electrons. So if you recall, we started with 32 electrons, that's our total, and then we're going to subtract 4 lots of 2 because we've got 2 electrons to form each bond. So having done that, 32 minus 8, it gives me 24 electrons left over to finish everything else off. So the other task I have to do, other than connecting my atoms together, is to finish the octets or duets on all of the atoms. So what we're going to do now is we're going to add lone pairs to complete the octets of all of the outer atoms. So in my case, I'm going to add 6 electrons as lone pairs to each of the 4 outer atoms. And we want to go ahead and subtract that number of electrons that we added to complete those lone pairs from the electrons that we have left over after step 3. So after step 3, once we'd made all the bonds, we had 24 electrons left to play with, and now we put 6 electrons on each of the 4 atoms, so we've got to subtract the number of electrons that we used to complete the octets of our outer atoms. So having done this, we realize that we have 0 electrons left. And what that means for us is that if anything is not correct at this point, if anything is not the way that it needs to be, I can't add any more electrons. All I can do is move electrons around that are already there. But what you want to keep in mind is that step 5 is if we had any leftover electrons at this point, we would put them as lone pairs on the central atom. Now, of course, in this case, we have no remaining electrons, so step 5 is not needed. The final step, step 6, is to check if the central atom has a complete octet. And in this case, it does, because it has 2, 4, 6, 8 electrons around the central carbon. Now, if we had a different scenario, say for example, something more like this, when we check the whether the central carbon atom here has an octet, we see that it only has 2, 4, 6 electrons around it. So to finish this off, we have to bring in a lone pair and make a double bond, and now our carbon has an octet because we have 2 electrons being shared here, another 2 electrons being shared here, and then 4 electrons being shared with the oxygen. In this case, however, our central carbon atom already has an octet, so step 6 of making double or triple bonds is not needed. So we should have a look at a molecule that has a double bond or 2 in it. So we're going to write the Lewis structure for carbon dioxide. So our first step is to count up all of the valence electrons. So just remember, carbon is in group 4A and oxygen is in group 6A. We have 1 carbon atom, so we get 4 electrons for the carbon, and we have 2 oxygen atoms which each contribute 6 electrons. So 4 plus 12 gives me 16 valence electrons to do all of the work with. So now we have to decide what atom goes in the middle. Well, as we mentioned before, carbon is in group 4, oxygen is in group 6, so 4 is smaller than 6, so carbon goes in the middle and the oxygen goes on the outside. Now, the central atoms have to be connected by at least single bonds, so we can go ahead and put in place the single bonds connecting the oxygen atoms to the carbon atom. And each of those single bonds consumes 2 electrons, so we should go ahead and subtract away 4 electrons from our total, which leaves us with 12 valence electrons to finish everything off. Step 4 is to complete the octets of our outer atoms with lone pairs. So we're going to put 6 electrons on each of our 2 oxygen atoms. And that's going to consume all of our remaining electrons. So step 5 is to replace any leftover electrons on our central atom, but we don't have any leftover electrons, so step 5 is not needed. Now here's the bit that I wanted you to see, is that we now need to recognize, got a little bit of ahead of myself, that for step 6 we've got to check the octet on our central carbon atom, and at the moment we only have 4 electrons around our central carbon, so that means I need to bring in another 4. So what I do is I bring in 2 from each side, and I make each of my bonds to carbon become a double bond. And now when I check all of this, we can see that every atom has an octet, and that I've used up the appropriate number of electrons. So we wanted to use 16 electrons. If we count up the electrons, we can go 2, 4, 6, 8, 10, 12, 14, 16. So that is correct. And if I check the oxygen on the right, in 2, 4, 6, 8, it has an octet. And if I check the oxygen on the left, 2, 4, 6, 8, it has an octet. And if I check the carbon that is in the middle, 2, 4, 6, 8, it has an octet. So once you've done a bunch of these, you'll observe some patterns. Typically what you see is the elements from group 7A, they tend to be on the outside of our molecules and form one bond, but not always. Oxygen atoms most often form 2 bonds, sometimes 3 though, occasionally 1. Nitrogen atoms most commonly form 3 bonds, and carbon atoms most commonly form 4 bonds. So we're going to practice a little now. So we have O2. So oxygen is in group 6A. So 2 times 6 means that we have 12 electrons to work with. Okay, so what's our central atom? Is it oxygen or is it oxygen? I guess it's oxygen. We'll call the one on the left our central atom. We're going to connect that to our outer atom, and that's going to use 2 electrons, leaving us with 10 to finish everything off. Now we're going to complete the octet on our outer atom that uses 6 electrons with 4 remaining. We replace our remaining electrons on our central atom, and then we check the octet of our central atom, and at the moment it has 6 electrons around it, 2 there, 2 there, and 2 there. So we need another 2 electrons, so we're going to bring in a lone pair and we're going to make it a double bond. So we get rid of that lone pair and bring them into there, and there's our Lewis structure. Now, C2H4 is a little bit more difficult. The hydrogens are going to go on the outside, and the carbons are going to go in the middle. How many electrons do we have to work with? 2 times 4 for the carbons, because carbon's in group 4A, and then 4 times 1 because hydrogen's in group 1A, so that's 8 plus 4. That gives me 12 electrons. We're going to connect everything together with single bonds, and so we've used 2, 4, 6, 8, 10. So take away 10 electrons, and that leaves us with 2 electrons remaining. Now normally we would complete the octets on our outer atoms before placing any electrons on our central atom. However, in this case, hydrogens already have a duet, so we can skip that step and we replace the last 2 electrons, leaving us with none left, on our central carbon there. So now we check that we have 2 central atoms in this case, that each of them has an octet. The one on the left, 2, 4, 6, 8, it does. However, our carbon on the right only has a share of 2, 4, 6. So we know what we need to do. We need to turn that lone pair into a double bond, and then now every atom has an octet or a duet. So every hydrogen, I hope you can see, has a share of 2, and every carbon has a share of 2, 4, 6, 8, 2, 4, 6, 8. So that everything is good. If we count up all of our electrons, they should add up to 12. Let's see what we get. 2, 4, 6, 8, 10, and 12. So everything looks good about both of our Lewis structures. Okay, so now we're checking for validity of a Lewis structure. There's 2 things that you want to check for. You want to check the number of electrons is correct, and you also want to check for octets and duets. So our first molecule is N2H2. So nitrogen's in group 5A, hydrogen's in group 1A, So we should have a total of 2 times 5 plus 2 times 1 equals 12 electrons. So let's have a look at this. How many electrons do I have? 2, 4, 6, 8, 10, 12. So our number of electrons is good. Now I want to check that every atom has an octet. Well, the hydrogens only need a duet, and they have that. This nitrogen atom here has 2 electrons here, 2 electrons here, and then another 4 electrons there. So that nitrogen is good. And then a similar scenario for the other one. It has a lone pair, which is 2 electrons. It shares 2 electrons with the hydrogen, and then it shares 4 electrons with the other nitrogen. So it looks like every atom has a complete octet that is not hydrogen, and the hydrogens have a complete duet. So I'm going to say that this is A is a good Lewis structure for this molecule. It has the correct number of electrons, being 12, and it has every atom with either an octet or a duet. Now let's look at the next one and see if we can spot what's wrong with it. So we've got H dash N triple bond N dash hydrogen, and there are no lone pairs. So it should add up that we have 12 electrons here. So we've got 2, 4, 6, 8, 10. And you can see the problem, 10 electrons is incorrect. Okay, so we know that this one is no good. Right, let's check C. The first thing we're going to do is we're going to check the number of electrons is correct, and then we're going to check octets. You can probably see already that this one is incorrect because both of the nitrogen atoms have 10 electrons around them. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And 10 is not 8. If we count up the number of electrons, we have 2, 4, 6, 8, 10, 12, 14. So we know it's wrong because 14 electrons is incorrect, and also nitrogens don't have an octet. So we can scrub C as well. So if you do decide that A is the correct option, you should always check the other ones. And like I was saying, the two things you always want to check, the total number of electrons adds up to be the correct number, and the atoms that are not hydrogen have an octet, and hydrogen has a duet. Okay, so that concludes section 4.3 regarding drawing Lewis structures.